All right, welcome back. Or what happens on YouTube? Hey guys, welcome to my video. Welcome to my channel. Anyway, isn't that always how they start? Hey guys, even though I'm trying to stop saying guys, I struggle with it. Welcome back. It's great to see you, both in person and for those of you online, good to see you too. Bayes. So, Bayes, how's Bayes going for you? It's a new week. I thought I'd check in. Just give you some updates first, and we'll check in a little bit. We'll move on forward. All right. First, class project. We're still going to have a class project. I'm planning on, after this homework is done, that to be your next assignment, and it's the preliminary idea. So I'll put more detail about that when we get closer to deadline. So by the end of next week, I'll show you what I expect. I'll make it an official assignment in Icon, so you'll get all the details for it and how to submit it. But basically, you just have to pick an idea. You can work in pairs. You don't have to work in pairs. You work by yourself or in groups of two. Structured that way strategically because I feel like in a group of two, you probably put in more effort than a group of four. And it's not that I want you to put in effort. I just want everybody to be learning. That's the main thing. I trust that you're putting in effort, and I will continue to do so. And it'll just be basically, what do you want to do? It could be a data analysis. It could be, let's take what we're learning in class and put it specific to you. Wide flexibility. Or it could be complicated, more complicated than that. Anyway, that's coming up. So it's going to take the place of the next homework that would come out. And it also occurs, I think it's October 12th and 14th. I'm not in person. I'm at a conference in Monterey, California, and that means that you can use that time from class to write up a little document for it. There's still another formative assessment out. Icon should have notified you. I'm assuming it did, but if it didn't, let me know. Let's do it noon Friday, or a little before noon. And then, of course, there's homework 2. Now, I wanted to mention something about homework 2. There's some questions in there about R squared and forming quantities. It's the basis of this next lecture. If you're really interested in energetic, you can skip ahead to it. It's at the end of the lecture. But I will tell you that if you wait until we discuss it in class, it may go a little bit better. It's just a few lines of code that I'm going to teach you how to do R squared, and it's going to happen within Stan. So I know many of you are working on it already. That's excellent. That's great to hear. And actually, if you haven't started yet, that's fine too. You still have time. But if you on those questions that may have to have you compute something, hold off on those until we get through this. I want to reiterate, that's part of the challenge of this class. It's hard to cover all the material that keep you working on or learning and how to do it itself. And I'm struggling trying to figure out how best to integrate both. So it will be fair. Yes?
I don't know if this would be helpful, but I'm kind of like trying to figure out what I want to do for the project. So if there's I know you had mentioned EFA, innovation indexes like that,
yeah.
But if you have other ideas, can you post that on Icon?
Yes, yeah. Let's do this. How about next week on one of the class periods, I just share my list of whatever random things that popped in my head.
Okay.
You can use that as inspiration. Alternatively, as a fallback, if you have a set of data that you want to analyze, if you just do an analysis on a set of data with Bayes or Stan, whatever, that counts as well too. So just if you're thinking of that. And if you want to do the data part and don't have the data, I can help you. I have data. I'm just kidding. I was about to say something like, I will take Lisa's data and give it to you. No. Just kidding. There are lots of ways of doing analyses with lots of data, and I'm happy to share whatever I have and whatever resources online that have them too. But thank you for asking that, and I will try to make a point of doing that next week. Okay. Also, I hear that the homework may have some typos in it, and I apologize for that. Let me grab that real quick. It appears a couple questions are repeated. 9 and 10 and 11 and 12. I will repost the homework deleting the repeated questions. There will not be additional detail, but basically you can just delete off them. Keep the numbering the same if you want. If the question 10 and question 9 are the same, question 12 and question 11 are the same. So you only need to answer one of them. So if you don't want to change your homework file because you're putting your answer in places, just delete one of them. It's okay. Yeah.
Can you explain the meaning of question 11 or 12?
Yeah. So in model 1, you run a linear model. We're going to learn about how you get an r squared. But for right now, let's just say there's r squared. Right? In model 2, you put in additional predictors, interaction terms. You have a different r squared. What question 11 is saying is what is the change in your r squared? And I'm specifically mentioning what we're going to talk about as we get into the lecture this week is for everything that we do in a Bayesian analysis that involves the parameters of the model, we will seek to find a posterior distribution of it. R squared is one of those things, right? So when I say the EAP estimate of r squared, we're talking about the mean of its posterior distribution. How does it shift when we add in predictors? That's the key. Hope that answers your question. Thank you. Okay, other questions? Yeah.
When we put sigma in as a sample parameter, is that already squared?
No, it is
Okay.
unsquared.
Okay.
And that's the one thing that actually is a nice reminder when you use different software to do whatever. When people form a distribution, you have to check what the parameters of it are. In Stan, it's just the standard deviation that goes in.
Okay.
In other, like in JAGs, it would be actually 1 over the squared. So it becomes complicated. Thank you. Yes?
I have a question on how we calculate the slopes
Yeah.
for a given value. So we have the model has beta 0 and 1 beta for the one factor at the reference value.
Yes.
And the other one, and then we have beta for when the values change.
That's right.
And a beta for the interaction.
That's right.
So if I have a value with an interaction, if I want to calculate the beta for not the standard
That's right.
value, so I have to add beta 0, beta for the factors, beta for when the factor is changed, and beta for the interaction?
Possibly. It depends.
Okay.
We are going to, so that part of it is also going to be covered at the second half of this lecture this week, which probably will come Friday.
Okay.
So if you really need to know, come talk to me after class.
Okay.
But otherwise, if you could hold off till Friday, I think you'll still have enough time, hopefully, to implement it in the analysis itself. Okay? I apologize again. Trying to get all the details out is tough, but we will discuss it. The basic, let me just give you the outline of the basics for it though, right? You sort of have to write your model down, you have to figure out which slope is which, and typically that would be it in a least squares analysis, but for us, what you're gonna have to do, with that information, you have to get it into Stan to have Stan do it for you. Okay, and the reason why we put it in Stan is because, well, actually there's two reasons. One, it's easier. It's just all embedded in the output object. But second, then, if we can make Stan work right, it does the calculations for us, and we don't have to worry about the weirdness of the Markov chain saved in the object. So it's coming. We'll have more of a discussion of that as we get to that part. Okay. Thank you for your question. I apologize for not having all that detail, but I really wanted to get this homework out this last week. So, thanks. How is everybody doing Bayes-wise? I assume, how many of you have been able to get Stan to at least run one of the models? That's good. That's good, right? So that's the hardest, honestly, that's the hardest part, is getting it run the first time. I know that sounds weird. The rest is like tedious, like lots of detail, but it's not as, like for me, it's always overwhelming to get my data in and results out. So if you can do that, that's perfect. That's what I want this to be. The other thing is, this is a psychometrics course. Where's psychometrics in this, right? We haven't gotten there yet. There are a few other details about Stan and Markov chains I've chosen to emphasize with linear models because those details still are similar. Concepts are still similar when we get into psychometrics. Remember, the tie with psychometrics is that psychometrics is like a multivariate linear set of linear models, right? Each item or each observed variable has a measurement model that goes with it, and it's basically a regression or a linear model. So for what we do in psychometrics, the concepts we're talking about here maintain. What should a prior be? How do Markov chains run? How do you specify them? What's the code like? All that still continues. And then today's lecture, here, I keep calling it, like we had lecture 3, but then all these are auxiliary topics that keep popping up. This brings a little bit more detail to it, to the analysis as well. We're going to talk about how we create efficient stand code, and then something called generated quantities. But most likely this lecture will cover both weeks. So I'm trying to get all this understanding into you. When we flip the psychometric switch, the psychometrics actually are less problematic once you know all this. It becomes then, okay, this is a different type of model. How do I specify it? And how do I get the model going? Sound good? Sorry it's taken so long. But this is I mentioned this is a challenging course. This is a challenging course for me to teach, but I'm enjoying it. I like a challenge. Anyone else like a challenge? That's right. That's why you're here in grad school, right? Okay. So do you recall where we left off last week? By the way, last week feels like a year ago. In between last week and this week, my in-laws came. They're good. It's all fine. But, but you know, like the weekend wasn't the typical cadence for me. We had left off talking about the impact of a prior on a model, and I wanted to continue that discussion for just a little bit. I had one more model I wanted to share with you in that example 3E code that's online, because I wanted to talk about the choice of prior. Now, I'm allowing you to choose your prior for the homework however you see fit. And I'm doing that because guess what? In the Bayes analysis, you have to pick it. I may pick differently. In fact, I will pick differently than you. But that's okay. That's how Bayes works, and we should be expecting that differently. You will not get penalized for your choice of prior. Okay? Okay. But do you remember what happened when we added the exponential for sigma? We could quickly see that we could change the way data looked, right? Even though we added the prior distribution for sigma, we saw that the standard errors, or the posterior standard deviations of our other parameters started to shrink. Right, and that's sort of kind of the interesting thing about priors in Bayes, because a lot of these parameters are tied together, right? If you have a smaller, in a linear model, if you shrink the residual standard deviation, or the residual variance, you shrink the posterior standard deviations. They're tied together. The next model here, though, is going to put a prior on our regression coefficients. In fact, you can see I've coded the prior that says normal 0, 1. We're saying each one of them follows a standard normal distribution. What do you think is going to happen when I do this? Yeah? Do you think that's a informative or uninformative prior?
Informative.
It's hard to tell, isn't it? Because it's all a relative measure. Right? How about we run the analysis and then we ask those questions? Think about this. Yeah.
But in this case, usually I think that we will not assume distribution for predictors, right? This is just a demonstration, or?
No, so these are not predictors. These are the regression coefficients that multiply the predictors.
Okay.
Yeah, so interestingly, if you look at our model here, we are putting prior distributions in for every one of the parameters and then for the outcome. But you're right, we don't assume a prior about the predictors, and they're not even specified. It is, the predictors are just given. Everything's conditional on that you observe them, and we're basically saying, I don't want to know what their distribution is. I don't really want to know. Now, there are ways that we could add that in, and in some actual psychometric or multivariate statistics we do, path analysis often puts some type of assumption about predictors. But for this, we have not assumed anything. All right, I'm going to run this analysis because I wanted to share with you what happens. So give me just a second to load up Stan here. No, I don't need that. Do need you, and I need these ones. This is where we need some like stand music to make this go. Actually, while I'm doing this, I'm going to share an anecdote with you that happened in front of you, Vladimir, today. I always tease Dr. LeBeau about the tidyverse, probably more than tease. I overly express my opinion when it's not warranted. How's that sound? I overshare my opinion. How's that sound? And Dr. Aloe said to me today, yeah, well, you know how you tease Dr. LeBeau about tidyverse. That's how I feel about you and Stan. So I'm not a Stan, all right? Sorry, that's a joke. Old man joke. I just wanted, like, I think of all the options, Stan is probably the best developed. That's where I'm at. That doesn't mean I love it, but I'll just say that. So I was surprised. Stan is my tidyverse. Oh, need the data. Dude, get your data. Quit telling stories. Nope. There we go. All right, let's go to Model 4. Sample this thing. Now let's take a look. Okay. Look at those parameter estimates. Do you remember what the betas were before? Yeah, actually, let's find out. Let's try Model 3 real quick. Oops. In just a moment, we'll have it. Okay, so Model 3, that was the model where we put the exponential prior on sigma. Right? So sigma's value was smaller than what we saw with Model 2, which is where we had the uniform prior. Uniform prior, this estimate was like 8 point whatever. Exponential prior, 4.7. So our betas, the point estimates, the EAP, the means, did not change. Right? So 148 for beta 0. Now let's take a look at that for Model 4. And actually, I can do, well, no. Model 4, beta 0 is now 0.248. That's a big difference, right? What do you think? Also, take a look at sigma. It went from a value of 4 to a value of 147. So what happened? Why did that happen? First of all, did you expect this?
Well, didn't we assume that the priors were normal with 0 and standard deviation 1?
That's right. Those are relative to our data. Remember, our data has a say in this too. With 30 observations, a normal 0, 1 put a very big influence on our parameters. Right? So what it's telling us is each of these parameters moved off of where they were before and moved towards 0. Right? So we've shrunken the parameters. And going from a value of 148 to 0.248 is pretty crazy. Right? That's a big impact, right? So you would see that's not cool. Sorry, if you're running this, that's a little weird. What about sigma? Why is that so big? It grew. Yeah, sigma is what tells you, quantifies how far off your prediction is from the actual value. And so when our parameters are saying, are way off from what we thought they were when we didn't put priors in, there's a whole lot more distance between what we predict for each observation and what we observed. And so sigma is picking that up, even though we have a prior on sigma that has shrunken it before. So it's interesting, what I'm trying to get you to think about is how all each of the model terms fit together. This is actually the coolest part of the course for me, is not that it's Bayes, it's that you have to learn about all the model parts and how they fit together. Like, I feel like it solidifies your understanding of models much more, because you can manipulate things and see how they break. This is not good. So, the question I have for you is, how would we know which one's more appropriate for our data? We don't know yet. I haven't introduced that. That's a topic I'm actually going to put off until next week. Why do things today when you can put them off for later? No, I have a lecture I'm trying to get through to describe all these other concepts. And that last lecture talks about what we call model fit. How do we evaluate whether a Bayesian model fits the data in an absolute sense, the data we've observed? with respect to priors, additionally, how do we evaluate which model seems to be more appropriate than the other? Now, again, we have to caution all that. None of this is going to be like, give us the answer that we're seeking, because all of it will be dependent on this sample. We have a sample of 30 observations. Generalizing our result may not be effective. Right? If we had 300 observations, what you would see is something very different with this result. By putting priors on, we would have, it would be much less of an impact. The data would have more of a say. So you can see how that works. Do you want to see what happens if we change?
Sorry,
Yeah.
even with the super strict prior distributions, if we had more people, these would move closer to the thing.
It should, yes.
Okay.
It's always a juggling act. How strict is the prior? How much information comes from the data? Because remember, the posterior distribution has two components always, right? The data and the prior. You want to see what happens if I change one of these? What if I made one 1,000? Like beta 0, let's put its variance to be, or its standard deviation. Remember this, in STAN, the second term is the standard deviation. A standard deviation of 1,000. What's that saying? Normal distributions are fun to work with, right? Plus or minus 3 times the standard deviation gives you about 99% of the mass of the distribution. So what we're talking about is 0 plus or minus 3,000, roughly. Right? So we're putting our stock into believing that beta 0 is somewhere between negative and positive 3,000, and most likely somewhere in the smaller range than that. So that actually begs the question, when you're building priors, what would you expect beta 0's range to be? And this is particularly important in linear models. It's less so in psychometric, but it's more important in linear models. What is beta 0?
Intercept.
It's the intercept. It's the predicted value of weight when everything is, when all the predictors are equal to 0. What is the units that beta 0 represents?
Outcome.
Units of the outcome, that's right. So in our case, they're weight in pounds. So when you're setting your priors, you ask those questions. What are the units of the parameter that we're working in? Those are the very basics, right? In terms of weight in pounds, we're all human beings. Many of us use pounds, although I think centimeters, or not centimeters, grams, kilograms are better. Can't even say what that is. But we've all stepped on the scale, and we all know what people weigh somewhat. Maybe not exactly, but in the ballpark. I can tell you that we don't need the prior to be negative, right? But we put it there. I have it there. That's probably not a good idea, right? So let's see what happens when I run this real quick. The other thing you'll notice, if you hard code the prior within the STAN syntax, by hard coding, what am I meaning? If I tell it it's 1,000, then you have to recompile STAN every time. The next step of this lecture, the next lecture, talks about ways that we don't have to do that. We can make it a variable, and we can submit the prior values as part of our data, and then STAN doesn't have to recompile. So it's sort of efficiency. But let's see what happens. You ready? There we go. Now beta 0 is at 170. It was, I think, at 168 when we didn't have the prior. What do you think? That seems more reasonable. Now those other parameters are a little bit screwed up. Do you have a good term to use for parameters that aren't quite what you think? Screwed up? Wonky. I like that. Wonky's good. All right. Last question. I ask this because, again, you have to sort of know your model to do Bayes in ways that are more appropriate. What is the scale of this height slope? It's a rate, right? It's pounds per, it's units of the outcome, so units of the outcome is pounds, I don't have it up here, per units of the predictor. So in this case, it's inches, so it's pounds per inch. That's really going to be difficult to figure out, right? Why is that difficult to figure out? Because we've got something that has its own scale in the numerator of that ratio, and something that has its own scale in the denominator. This is where I need to tell a quick story. Many of you have taken chemistry before. You remember a part of chemistry called stoichiometry? I failed chemistry in high school, by the way. Straight up failed it. Got to community college, realized I could do school, loved it. Anyway. But there's a part of it where they talk about canceling units, canceling rates, and so forth. And that's sort of there's nothing canceling here, but what you have to think about is the rate. It's really hard to do. So what you have to remember is that parameter itself, that when you put a prior on it, you can quickly pick a prior that becomes unintentionally way more informative than you want, right? So in a linear model, each of those parameters is going to involve something about the outcome and something about the predictor. And that's really difficult to anticipate what those are. So when I look at a linear model from a Bayesian perspective, the units that are described by beta height are very different than the units described by beta group 2, right? Beta group 2 is a grouping variable. It's dummy coded, so it's a 0 or a 1. This reflects the difference in weight in pounds for someone who's in group 1 versus someone who's in group 2. That's a different scale altogether than beta height, which is now units or pounds per inch. Right? So all of that, if you're going, oh, this is really confusing, yes. So what does that mean? Do the least amount of harm. That's my philosophy. Right? Think about using priors that are very uninformative. Or the choice of a uniform prior across the space of it. It's fine. In a linear model, it's critically important because each of those parameters have different scales, have different units attached to them. Now, ironically, because this is a psychometric class, when we think of the linear model in psychometrics, it's a little bit different. Right? The intercept is still in the units of the outcome. But the outcome could either be, let's take a confirmatory factor analysis. Right? It's like a Likert style item is usually what the outcome is, right? 1, 2, 3, 4, 5 are the numbers. So you know the intercept's going to be somewhere in the middle there, most likely. 1, 2, 3, 4, or 5. Okay, that works. And it's going to be like that for all the items that have that scale. The slopes, or the factor loadings and so forth, are going to be in the units of the latent variable, or units of outcome per unit of latent variable. And that latter term is something we're going to have to define ourselves. But once we define it, it's the same. The denominator of that rate is the same across all the items where that latent variable is measured. So in this respect, a psychometric model is actually a much more simplified version of the linear model. But when you're entering priors, when you're thinking about priors, the point of this example right here is to make you think, the first question in mind is, what is the likely scale of that parameter estimate? Right? What's the range likely to be? And then how do we go and make sure that we do the least amount of harm? Because for our small sample data, putting a relatively uninformative prior on it causes all sorts of issues. Okay, questions on what I just said while I change some code? Okay, what I'm doing is changing the priors so that we have a very wide distribution for each. I don't know if this is sufficient, but let's try it. I suspect it will be. Again, it takes a couple seconds to compile. And here we go. Now, those numbers look almost like our very first analysis. Right? The previous set of numbers, remember, beta 0 was 170. These all numbers were whack, was it? Is that the term you said?
Oh, wonky.
Wonky. Wonky, whack, wonky. These other terms were wonky. That one was a little bit better. But now all of these start to look the same. And the point of the matter is, remember, all these parameters are in a model, the parameters of a model are tied together in ways. So, again, I'm giving you why my philosophy is do the least amount of harm with your data in Bayes. The more uninformative the prior, the better the more relieved I am about it. But if you insist on using priors, showing how sensitive your analysis is, trying a couple different types or a couple different standard deviations is a good way of providing evidence that what you're doing is the least amount of harm. So, how are we doing?
Jonathan,
Yeah.
when you're picking a prior, so would you ever look at like a general mean for what, so like we're looking at weight, right?
Yeah.
And we were saying, I mean, people don't weigh 1,000 pounds, people don't, you know, so would you want to consider that? Because you're saying to have the most uninformative, but if we know this, wouldn't you want to put it in there?
Yeah, I think that would be the case. If you think about what the prior might be for a beta 0, right? We might say this is uniform or log normal or something that would be strictly positive, right? Alternatively, the way that we sort of looked at this before, if we were to plot the prior distribution and just look at its height over the range we expect the parameter to be. So let me see if I can do that really quickly. But anyway, just yes, the answer is yeah, we may want to consider that, but I think it's a little bit more complicated than that in the abstract. Let me just try this. Let's see, plot y equals d-norm of x, actually hang on here, values from 0 to, let's say, I don't know, let's give a range, 0 to 400 pounds in 1 pound increments, okay? And we want the mean of this thing to be 0 and the standard deviation to be 1,000. And x will be the sequencer. So this may sound kind of ridiculous, but what I'm trying to do is plot the shape of this distribution, the height of the distribution across the expected range of the parameters. So what am I doing this? Our parameters in their posterior distribution are going to start to converge somewhere to where weights happen to fall, right? And you know, for most of our purposes, they're somewhere between these numbers here, right? Not always, but most likely, right? And so what is the relative impact of the prior for each across that range is what we're asking. And here, the curve looks really big. Like, whoa, look at that curve. But take a look at the difference in values. It changes only in the 5th decimal spot, right? So what's that telling us? Like there's like the contribution of the prior across this range, even if we pick something that doesn't quite fit exactly with what we want, like we know this normal distribution, it goes negative, weights are certainly not going to go negative. But the amount of information that the prior is including across this range is relatively small, right? And that's the key to thinking about it. It's sometimes a prior may not fit that range well, but may not be doing a lot of harm because it's so there's so little difference in the height of the prior for someone who's across the range of the expected value, or the parameter statistic. Does that help answer your question?
Yeah, so can you explain why you chose 1,000? I know it was a random number you chose, but why would you choose 1,000 versus 500? Because in my mind, I would think 500 would be better for weight, but I don't.
I agree. You could pick either. I picked it because I was going for a big round number. Yeah, that's it. And I had worked with normals a number of times. We work with normal distributions a lot, particularly generating data. So just my own experience with normal distributions is it's a wide parameter. 500 also has that. And the difference is now appears in the 4th decimal place. So let's do this. 10th, 100,000, 100,000. So like 1,500 thousandths of a fraction. We're talking not much, even at 500. So that still would work. So, but here's the thing. You asking that question and me starting with a prior and you starting a prior is absolutely the right, what happens some days, right? We argue about priors a lot. The reality is, just if I show you what happens, let's just try the 500 out. For models that don't take long to run, it's fairly easy to entertain several of these priors because You can just see what the impact happens to be. Although it may take longer to compile than run here. And see with a 500 prior, the numbers aren't that much different either. So at some point what we're saying is, between the two of us, we both may have a different impression of what uninformative is, but both of those are fairly uninformative. So probably neither is going to make a difference. Did that help?
Yeah, and so next week we're going to be talking more about model fit and
Yes.
how to, okay, so
Yeah.
I'll keep those questions for next week then.
Yeah,
Okay, thank you.
we will try to quantify how close we are to our data in our sample. That's the goal of model fit that we're going to be getting to. So, but these are good questions to ask because the biggest critical issue in Bayes analyses typically is the choice of prior, particularly when your data are not numerous, when you don't have a big contribution of your data. So asking these questions is part of the scientific process, right? You think it should be 500 for the standard deviation. I said 1,000. Turns out we're probably splitting hairs there. We can both agree that a standard deviation of 1, probably not the right prior to use, right? Can we all agree on that? But of the range of priors that are out there, I don't know what the right prior is. My own hunch is do the least amount of harm.
If it's do the least amount of harm,
Yeah,
why even have a prior
Agreed.
to begin with?
I'm with you. I'm with you.
Okay.
There's a camp of those who aren't, who say you sort of neglect the Bayesian process. I'm not one of them. I'm the agnostic Bayesian. By saying that the agnostic, not diagnostic, but I'm an agnostic. I don't subscribe to that the prior is the be-all and end-all of Bayes. I'm more like the idea that in small samples, Bayes, if we pick uninformative priors, may give us a more conservative result scientifically, right? And so that idea, for me, when it comes to reporting, because of some of the crises in science we've had in the last 20 years, particularly p-hacking and all the other things, where we sort of over-publicize the information in an analysis. I'm just going to boil it down to a very small, probably not entirely accurate statement. But I think if we do the least amount of harm, if we allow more conservativeness in our analysis, it'll drive us to make better decisions as we go further. That's a big belief of mine. But I'm giving you, you're taking this class from me. If you took it from, someone who drinks the Bayesian tea, they will be, no, there has to be the prior. There are these special cases where this happens, or this happens, or this happens. And I'm kind of like,
You're drinking like the hot lemon water.
yeah, maybe that's it. And this is one of the criticisms of Bayes. Like, why would you use this if you can pick a prior and I can pick a prior and we come up with a little bit different answers? I think if you get through that part, it's really powerful, right? Because some of the answers we can do are appropriate. I like the description of credible intervals. I like saying, that we think the parameters in this range, rather than if we repeat this experiment X number of the hoops we have to jump through otherwise. We haven't talked about hypothesis testing. But if we were to form that as well, we might have a prior for hypotheses, and that all of a sudden changes things as well too, potentially. But anyway, how's this going conceptually? Again, all this is important because we're going to need this in psychometrics as we go too. I feel like I'm like,
Can I ask one more question?
absolutely, go for it.
Sorry. I'm wondering why it automatically, if you don't put in a prior, it automatically goes to uniform instead of, is it because you have to specify the normal parameters? I'm thinking like in general in statistics, the central, what is that theorem called? Where everything sort of ends up in a normal. Why would it not require you to do that?
So
why is it?
There's certain asymptotic, there's several series of parameter or theorems that talk about when you have a certain estimator, the estimates themselves converge to normal.
Yes.
But I think you're right. I think from a software perspective, when you don't specify something, the uniform's going to run, so you let it run. Right?
Okay.
It's sort of
okay.
It's a very harmless default. And yes, those people who are more authentic Bayesians than me, although I did go visit the gravesite of Bayes, so I'm plenty authentic. But those who are more than me would quibble about it. But the analysis still runs, and it's sort of less complication in the analysis. So getting it working is easier that way. I don't know other than that, though. I'm pretty sure, Andrew Gellman, who was sort of one of the principal architects of STAN, is one of the better statisticians of our lifetime, actually. He has a blog. He may have put on there why they chose that. Puts a lot of thoughts on there. So people start citing his blog. That gets me a little sideways. Well, Andrew Gellman said, yeah, I get it. And usually he's well thought out about how he says things, but a blog post isn't usually the place where you can get all the well thought out details as to why someone would say something. So. Anyway, I have a lot of respect for him, even though he and I probably would differ quite a lot on how we would choose to do an analysis. So. Okay? Any other thoughts on priors? Okay. Shall we dive into the actual lecture from this week? This is lecture 3B. I put up these slides here in HTML, and I noticed you may have had hard times printing these slides, and I'm sorry about that. That's me trying to get used to things. If you go to the slide site itself, I wanted to show this to you real quick. And you hit the little three buttons at the below that under this tools window, there is a PDF export mode. You click that and you print from there with your system printing, and it prints better. Now, I wouldn't say it's like glamorous, but it prints better. So I say that to you if you're interested in printing the slides yourself. What I will try to do, time permitting and my memory not failing me, is provide that PDF for you in the analysis itself. Now, again, you can see it doesn't quite render it perfectly, but it's at least, actually, you can't see that. It's on my side.
It doesn't seem to print the images, like the graphs.
That is a problem. Hey, that image did. But yeah, I'm not sure why that is. So I apologize for the struggles with this. Yep. Okay, I will work on trying to get the images there. I'll try. Sorry about that. But I'll keep working on it. I know it's a problem. Do you like seeing the slides in our studio, or is that not worth it to you? I think I'm gonna put out a survey about what your thoughts are in class. I'm trying to be as good as I can as a professor about this, but I'd love to hear what your thoughts on this, because it's a little clunky, but anyway.
Well, the fact that for whatever reason we can switch the slides.
I fixed that. I didn't realize that was an option. Yeah, it turns out at the top of the code there's this multiplex option, and I had it turned on to true. And now I have it as false, and it shouldn't do that. But that thing, by the way, creeps me out.
It does.
It's like a Bluetooth ghost of some sort. And I'm like, how?
Somebody could exploit that.
Yeah, that's what I was wondering too. Anyway. All right. So, what are we going to talk about for the rest of the week? We're going to talk about how to make syntax a little bit shorter to write. And then we're going to talk about computing functions of model parameters. I know that sounds like two very different topics, but I'm doing one first and then the other because the shorter syntax will keep you from having to recompile STAN every time you change something. It'll also make your life a little bit easier as we go forward into psychometrics. Rather than having to write out every parameter, there's shorthand that we can do to make it work. Then, with that shorthand syntax, I will show you how we can then create functions of parameters efficiently to build things like simple slopes, or the slope of group 2 when it wasn't part of our analysis, or r squared as we go forward. So that's the goal. Stop me again if you have questions. Okay, so remember the STAN syntax from before. It was pretty long, right? We had a declared variable for each parameter. In fact, I can just pull it up real quick here. Look at that data section. We have a vector for each one of the variables. We had to then declare each one of our parameters as real or something like that. And then when we finally got to the model, we had all this going on. That's a mess too, right? How many of you made a typo there and had STAN say it didn't know what that variable was? It's a pain, right? So turns out STAN makes it somewhat easy to do this to shorten syntax. The method it uses is to define everything as instead of matrices and vectors. So instead of giving Stan as input singular vectors, we can put them all in a matrix, or put the outcome as a vector and the predictors as a matrix. We can then put our parameters into a vector, and then Stan will use matrix algebra to make a matrix product to produce the model. And then we can use that matrix product to do some of our other things that we want to do as well, namely model fit, that'll be next week, and functions, manipulations of the parameters themselves. And then finally, to do that, though, we'll have to know a little bit about multivariate distributions for specifying priors. That's where we're going. How many of you know a little matrix algebra? How many of you know none? That's okay too. Okay. I'm going to give you enough to make it through, but no more than that. So for the record, matrix algebra, I went to, I was a junior at Sacramento State in California, undergrad, and I had a professor tell me, you're going to go to grad school, just reach out to professors at your grad schools. Great advice, right? So I picked a few professors and sent them emails and said, what advice would you give me to sort of fill out my classes before I graduate? And then almost everyone, I got 2 responses from 3 emails, and almost everyone said, matrix algebra, take a matrix algebra class. And I did, and half of the class was just not what I needed. So I'm going to make it like the abbreviated version. The YouTube video of matrix algebra is right here, okay? Here we go. So that means if you're in math, plug your ears. This is my quick version of matrix algebra, at least for what we need here. The linear model without matrices looks like this, right? We have for each person, we have a subscript p for each variable. And we list all the variables, and we list all the parameters. And just to remind you, group 2 was a dummy-coded group. Group 3 was a dummy code, whether a person's in group 3, and then error follows that normal distribution. We're familiar with that. By the way, that's the path diagram I was meaning to show before. All right, outcome is weight. I'm sneaking this in because we're going to come back to path diagrams with psychometrics, and we're getting there, I promise. But what are we saying here? Height predicts weight, because there's a little arrowhead predicting weight over here. Diet group predicts weight. And now look what happens with this interaction. To reflect an interaction well in a path diagram, it's like saying there's a brand new variable we've defined, right? So it's a height times weight predicting. That's all. Okay, path diagram, done. We could go and actually start taking everything on the right-hand side of the equation, right? Everything that shows up over here, and building matrices and vectors with it. So let me define what a vector is. A vector is just an array of numbers, right? A matrix is a set of arrays that all have the same length, right? So if we had 30 observations, right? If you look at our Stan syntax here, each one of these things, we had to tell it how long it was. It was n observations. So each of these has 30 observations in it. So what we can do, instead of calling it a vector, is call it a matrix. Matrices have 2 dimensions to them, rows and columns, right? So each row would be an observation, each column would be a variable. Or another way of putting it, a matrix is a collection of vectors that all have the same length. Right? So it's a box. That's it. There's nothing glamorous about it. All the numbers are still there. Just a way of representing our data. Okay? Similarly, we could take all of our beta coefficients and put them in a vector. Now this is the hypothetical. This is what we're going to be doing coming forward here is we are going to send into Stan our model data matrix. But we're going to define in Stan our parameters as a vector. And why we're going to do that is going to come together in just a moment. Matrix product. Okay? How we doing? Okay. Again, this is, plug your ears, mathematicians, this is not matrix algebra for you. This is matrix algebra for us. So matrix, again, is a box of data, has rows and columns. A vector, you can actually think of a vector as a type of matrix. Right? There are 6 rows to this vector. There are 6 parameters. There's 1 column. We have to remember in matrix algebra, one of the things that we need to, the first things that we need to do to describe these entities is to talk about their size, because we are going to multiply these together, and matrix multiplication only works when the sizes conform to what we need them to be. So matrix has rows and columns. Vectors actually have rows and columns, where one of those is a 1. Right? This is a column vector. There's 1 column and 6 rows. Alternatively, we could have expressed this as a row vector, which would have been 1 row and 6 columns. Why and how matters little. It's more contextual. It's sort of to make algebra work once we get there. But it turns out R has built-in syntax to do the matrix for us. In fact, let me go grab the R syntax for this lecture. That's not it. Probably the most amazing function that you've never heard of in R, unless you work with me, is something called the model matrix. This is the previous stand code. In R, there's a function called model.matrix. What it will do is take your linear model. So this is our linear model before we had specified. And it will output something called a model matrix or a predictor matrix. This is what it looks like. Right? All of our observations, 30 observations, this is the set of predictors, and a column of 1s for the intercept. Last week, I think I might have called this a design matrix. More appropriately, design matrices are, that terminology comes from the idea of experimental design, where we would randomly assign people to certain groups. I have our grouping factor here, so it implies sort of a coding structure. A predictor matrix is a little bit less design-like, although we have a coding vector here, an intercept, and some other coding vectors otherwise. But this is what we will use to send Stan all of our data, is a model matrix. That makes it easy because now we wouldn't have to define 6 different vectors for each of the predictions. It also makes it nice because some of our variables are products. Some of those are interaction terms. And if you remember how we inputted the data into Stan, we had to form the product itself before we put it into Stan. This model matrix does it for us. It's built in. Seriously, it's amazing. So what we could do with that model matrix, if we define that model matrix as X, as our matrix X, it has, for our data, 30, actually we could ask for it. What are the dimensions of it? 30 is the first number of this dim function is the number of rows. The second is the number of columns. It has 30 rows and 6 columns. Remember, there's 30 observations in our data, so that's one row for each person. So we have X. We have then 6 coefficients. If we put that in a coefficient vector we call beta, it would have 6 coefficients by 1 column. So we can rewrite our linear model to reflect this, right? And it's actually a little bit more general than what we have up here. Sometimes this version that you see here is called the scalar version of a model equation. Scalar is the term for a non-matrix entity. Right? It's just a single number itself. The weight in pounds for a person is equal to this. That's scalar. If we put this in a matrix, if we looked at weight in pounds as a vector, right? This would be a size 30 by 1 vector. It would be equal to the matrix products of X, our design matrix, times beta, plus a vector of error terms, which again would be 30 by 1. And so what ends up happening in matrix algebra, let's see if I have it here. Yep. So to make this matrix product, right here, x times beta, what we have to do is we have to align the number of columns of x and the number of rows of beta. So a matrix multiplication, matrix product. This is the matrix algebra you need to do this, just this one term, right? It takes a matrix called the pre-multiplying matrix. That's x. It's size n rows by p columns. You can multiply it against beta if beta has p rows in it. And the resulting matrix is sized with the rows of x, the pre-multiplying matrix, and the columns of beta, the post-multiplying. So the result of this will be a n by 1 vector. Now let's talk a little bit about what goes into that vector. So here's the, that's not what I wanted. No. All right, here comes matrix algebra. You ready? We're looking at the matrix X and the vector beta. Now, when I write this, my apologies for my handwriting. My handwriting is poor. I know that. But when I do matrices, I put a little half arrow above them because I can't make my handwriting in bold. Typically, you see matrices in bold when you see them in text. But the way this works is we do the following. If this is X, I'm going to make X a little bit smaller. I'm going to make it, what is the size of X if I do that? We'll call this X right here. X has 2 rows and 3 columns. So it would be a 2 by 3 matrix. If we form beta, we know to make the matrix product X times beta, we need it to have the same number of rows as X has columns. So it needs to have 3 rows. And to make this simple, I'll just do this, 1, 0, 1. Okay? So let's do this matrix product real quick. A matrix product results, if I did x beta, it's going to be equal to a matrix that is 2 rows by 1 column. Right? And here's how the matrix product works. It takes a row, so let's start with this row right here, and it multiplies each element times the corresponding element in the first column of the post-multiplying matrix, right? So if I were writing this out longhand, it would be the following. It would look like 1 times 1, 2 times 0, 3 times 1. Then it sums those results together to produce the new value. So 1 times 1 is 1, 2 times 0 is 0, 3 times 1 is 1. So the value when we add those together is a 4. Okay? So let me ask you, what would the second entry be? That was quick. 0 times 1 is 0, 1 times 0 is 1. Oh, sorry, 0. 2 times 1 is 2. We're left with 2. So this is a really handy tool. By the way, had I just modified this slightly and beta made this a 1 here, it would turn out that this number would now be the sum of all the entries in a given row of our matrix. But I digress. Questions? That's the one trick about matrix algebra for today. So for those of you who haven't had a lot of matrix algebra, matrix multiplication. You have to have the right sizes of matrix to make it work. But when it does, it's this element multiplication and then a summation across them. So it's rows of x times columns of beta to make it work. So turns out R also has matrix algebra built in. Let me see where I put that in my code. Oh, forget the code then. All right, so here, whoops, I said there are 6 predictors. There's actually 6 coefficients. Why did you just go back there? 6 coefficients. There are actually 5 predictors and 1 intercept. All right? So I created a matrix beta. Let me find it. There. Where did I put you? Huh. All right. Forget it. I'll put you over here. So there we go. Okay, so with 6 predictors, I created in R a matrix called beta. R uses, so the terms we use in matrix algebra and the terms we use in R are slightly different. In R, to do a matrix multiplication, we need both objects to be what R considers a matrix, right? So if I do class beta, it's going to tell me it's a matrix or an array, right? The reason why R needs that is it needs to check the dimensions to make sure they align, right? So that we have the right size of x to multiply the right size of beta. So I just randomly picked beta terms here. So I created this beta vector. Then I created x based on our model matrix, right? This is our design matrix, or predictor matrix. We could then have R do the matrix product for us, right? So with one quick term, what do we get here? This turns out to be the product of each person's predictors times all the regression coefficients. Or another way of putting it, this is the predicted value for each person's outcome based on the coefficients that we have. So quickly we can say, wait a minute, forget this scalar notation. If I used a matrix in place of my predictors, and I used a vector in place of my coefficients, I could quickly describe everybody with one matrix product in code. That's the key about matrix algebra, and that's how Stan will speed up very, very fast for building code and syntax. How we do it? Okay. So let's go. So we just have to tell Stan what we're changing to make this work. In particular, can you see that okay font-wise in class? Okay. This is the old syntax. This is the new syntax. I'm going to tell Stan, basically, my predictors are all going to be in this matrix called X. But Stan needs to know the size of the matrix. So I'm going to say I have n observation and p predictors plus a column for the intercept, right? So it's actually p minus 1 predictors and then 1 intercept column. But because I'm saying n and p, Stan needs to know what n and p happen to be. So I define n as an integer. I define p as an integer. When you use the term matrix in Stan, it defaults to being a floating point number, so it's expecting it to be any decimal real valued number. No imaginary numbers, that's the main thing. And then for the outcome, I'm just going to leave it as a vector. It's just going to be a 30 or a size n vector that goes in. Again, floating point. How are we doing so far? Now, these other vectors and matrices you see here, those will be useful because now what we're going to code in the parameters section is we're going to tell Stan, don't give me one parameter per predictor, give me a vector of parameters, right? Remember in beta, when we're building when we talk about matrix algebra slightly before this, beta has 6 rows and 1 column. So we're going to tell Stan it's a vector. When we tell Stan it's a vector, we can't just use a univariate normal prior on it. We have to change our prior. So we end up having a few other terms that will matter for the prior. And I'll talk about those in just a moment. Questions on this so far? Okay. So now let's talk about that parameter section. Before, you had to lay out all the parameters in Stan. Here in our Stan model, I'm still going to let sigma be there for the residual standard deviation by itself. So that didn't change. But instead of having each of these betas, I'm now going to define a vector beta. But when we define a vector, we have to tell it what size the vector is, the number of rows in beta. and the number of rows is what we defined as the variable p to input into stand. P for predictors plus intercept. How we do it? Cool? Okay. So now let's talk priors, because when we get to model, we're going to want to put a prior, potentially put a prior on beta. And with a vector, it won't like the univariate normal. Yes.
Sorry, I do have a question about the code.
Yeah.
So we essentially have a column in our original data set that represents our predictors, and that's how it's gonna know what our, like, how many betas we
That's
have,
right.
essentially, right?
That's
Okay.
right.
Okay.
Yeah, so what you will be doing coming up, what I'm going to try to teach you to do, is you could form your linear model in R using this formula statement, and then based on it, your code can detect all the things that Stan needs. And then Stan will run, this syntax in Stan that I'm building here will run for any number of predictors with any number of observations, your simple linear model. So you wouldn't have to change your Stan syntax if you change your priors, if you change which set of predictors you're using, if you get different data, all this will work.
And we would change it with the model form, like
Oh, I just did it again.
the code you're building now is basically like, Stan doesn't have to essentially, we don't have to touch Stan.
That's right.
We would touch like line 128.
That's right. The data that
Okay.
goes into Stan will change, but the guts of Stan are the same.
Great.
So another way of putting it, we build one really general set of Stan syntax. We tell the compiler, compile this, and then we just do a bunch of different models by sending it different input.
Great.
It's using the same syntax, which means it's using the same compiled program. Because we can, this is sort of the idea of making the process more general for doing modeling. Other questions? Okay. So, let's talk about priors. All right? So each prior before, we have these, what we call univariate priors. A univariate distribution means one variable, right? So we could plot what the shape of the distribution is. We've got the range of the variable on the y-axis, or the x-axis. On the y-axis, we have the likelihood that comes with the prior distribution. Moreover, for the betas, that last example I ran, we had univariate normal distributions that were independent of each other. Right? If we go back to my syntax, where we were looking at each of these priors, when you specify it this way, you're saying the prior for beta 0 is independent or uncorrelated with prior for beta of height likewise, right? Well, it turns out there is a distribution that does all this for us. It's not really the most unique name in the world. It's the multivariate normal distribution. Not Iowa. How about we do multivariate normal? There we go. Let's go to Wikipedia. The multivariate normal distribution is a normal distribution for each variable by itself, and a bivariate distribution for each pair of variables. So this is a plot of two variables. Let's call this x and y. This could be like beta 0 and beta 1 for our parameters. What the distribution is characterized by is a generalization of what we had for univariate. Right? For a univariate normal, there were two parameters. There's a mean and a standard deviation. For a multivariate normal, there's a vector of means, one for each of the variables. And then instead of a vector of standard deviations, we actually want to consider the correlation or covariance. So it's a matrix where the diagonal of the matrix has the variance and the off diagonal has the covariance. So multivariate normal is our generalization of univariate normal, and it's characterized by two sets of parameters, two matrices of parameters, a mean vector and a covariance matrix. Okay? How are we doing? Now, here's the fun thing. If the multivariate normal is the only distribution that I know of that you can say this in general. If in your covariance matrix, the value between two variables is 0, the covariance is 0, those variables are independent. So the priors that we put in our example in Stan, in my R code here with independent univariate normals, we can come up with an equivalent set of priors with a multivariate normal if our covariance matrix does not have any values in the off-diagonal elements. Okay? So let me go a little bit further with that. So let me show you what I'm talking about here. So again, with matrices and multivariate distributions, we have to understand the size or the number of variables that are included in them. We're setting up a distribution for our prior. So the first question is, how many parameters are included in that prior? We have 6. It's the size of beta. So the first thing we need to know is what is the mean vector for those parameters? Well, if we follow along from the syntax from the previous time, that mean vector is a vector of zeros. Now, this is not the same R syntax where I had to put it in the matrix because Stan doesn't want it to be a matrix. So we're actually giving it a vector in R to input it into Stan. But every one of those reflects the mean or the prior value of the mean for each one of our parameters themselves. And they go in order of the parameters in the predictors, right? So this would be the mean of the intercept, the mean of the first predictor, second, third, and so forth, right? The covariance matrix is similar to that. Now, before I had 1,000, so let's just do that. The covariance matrix, though, is a matrix, and it's the size of number of parameters by number of parameters. It's a 6-row by 6-column matrix. Okay? Not only that, this is, you could go from a covariance matrix to a correlation matrix. You can always rescale from covariance to correlation. So this is like what you're used to if you're used to correlation matrix. The diagonal of the covariance matrix are the variances for each of the parameters. Actually, that's why I did that. In Stan, that's a variance, not a standard deviation. And actually, I put the wrong value in. It should be 1,000 squared for each of those. So how about I do that? There's our variances right here. Oh, no, don't do that. Stop it. All right. Okay, there we go. Nope. All right. Going back. All right, so this is our covariance matrix, cov beta. It needs to be 6 by 6 because there's 6 parameters. This is telling us the prior variance of each parameter. The off-diagonal is allowing us to specify a covariance between parameters. You may think, and that actually brings up an interesting topic. We talked about prior belief about mean being where we think the parameter be, and about variance being how certain we are in that belief, like how peaked our belief is. We actually can specify a new part of a prior in this, a multivariate prior that says we think this parameter and that parameter are going to be correlated. That's hard to do. Like it was already hard enough with mean and variance, so I left those as 0, basically saying that each one of these as a prior distribution has no belief that they're correlated. Weird? How are we doing with all of it? Good? Okay. We're almost out of here. I got 1 minute. In my minute remaining, I'm going to say the following. My Stan model, if you look at my Stan syntax for the priors, when I define the model for it, I'm going to define multinormal for a prior. It's going to have the mean vector and the covariance matrix. Our sigma prior is exponential. That instead of putting in the number straight into the Stan code, I'm going to import it as a variable. It's going to be in my data statement. By doing that, every time I change a prior, I don't have to recompile the Stan code. Right? I just change the data that goes into Stan and it runs. Finally, for y, I use a normal distribution, but Stan, if you define matrices and vectors and they're the right size, when you make them multiply each other, it's a matrix product. So it will be x times beta that shows up here. And then sigma still is the other term. This is much shorter syntax. And that's all I can say today. Okay, hang on 1 second. I'll take your questions after class. We're out of time. For those of you who don't have questions, I don't want to waste your time. Have a pleasant afternoon. Just pleasant. Maybe slightly above average. Okay? Positively skewed. Let's do that. I'll see you next time. See you Friday. We're going to continue with this where I just left off, okay? Okay.